All right. So let's learn about E. Let's see here.
We're going to talk about E, the big famous constant E. Okay, it's one of the famous mathematical constants, one of the most important. It goes along with pi and, I don't know, golden ratio and square root of 2. There are constants in maths that are the most important constants. And E is one of those constants. So E is an irrational number. It's equal to 2.71828182 something. The problem with E is it's not defined by geometry. Now pi is something that's defined by geometry, right? It's the ratio of a circle circumference and its diameter, and it's something the ancient Greeks knew about. And a lot of mathematical constants go back to the ancient Greeks, but E is different. E is not based on a shape. It's not based on geometry. It's a mathematical constant that is related to growth and rate of change. But why is it related to growth and rate of change? So let's look at the original problem where E was first used. So we're going to go back to the 17th century, and this is Jacob Bernoulli, and he was interested in compound interest. So earning interest on your money. So imagine you've got £1 in the bank. You have a very generous bank, and they're going to offer you 100% interest every year. Wow, thanks a lot, bank. So 100% interest, so it means after 1 year, you'll have £2. So you've earned £1 interest, and you've got your original pound. So you now have £2. What if I offered you instead 50% interest every 6 months? Now, is that better or worse? Well, let's think about it. Okay, you're starting with £1, and then I'm going to offer you 50% interest every 6 months. So after 6 months, you now have £1.50. And then you wait another 6 months, and you're earning 50% interest on your total, which is another 75p. Then you add that on to what you had, so it's £2.25. Better. It's better. So what happens if I do this more regularly? What if I do it every month? I offer you 1/12 interest every month. Is that better? So let's think about that. So after the first month, it's going to be multiplied by this. 1 plus 1/12. So 1/12, that's your interest. And then you're adding that onto the original pound that you've got. So you do that, that's your first month. Then for your second month, you take that and multiply it again by the same value. Then your third month, you would multiply it again and again. You actually do that 12 times in a year. So in a year, you would raise that to the power 12, and you would get £2.61. So it's actually better. In fact, the more frequent your interest is, the better the results. Let's start with every week. Okay, so if we do it for every week, how much better is that? Okay, what I'm saying is you're earning 1/52 interest every week. And then after the end of the year, you've got 52 weeks, and you would have £2.69. So it's getting better and better and better. In general, you might be able to see a pattern happening here. In general, it would look like this. You'd be multiplying by 1 plus 1/n to the power n. Hopefully you can see that pattern happening. So,
Okay, so sure, we're only really talking about £2 here, but what if this was in millions? Okay, so what if this was 2.61 million versus 2.69 million? That's a lot more money. So the idea here is the more often that you can compound your interest, it's free money. So the more often that you can get that free money, you then, the next time they go to calculate the interest, they are calculating the interest on the money that you started with and all that free money that they already gave you. And so the more often that you can do that, what ends up happening is that this value continues to increase. So let's say we plug in 10,000 for n. We're still going to get around $2.7. We're going to get closer and closer and closer to 2.718. Yeah.
So I'm guessing banks don't do this in real life.
Actually, banks do this in real life, but the interest rate is not 100%. Okay, the interest rate is more like 0.004. Okay, so it's significantly smaller. But absolutely, this is how the banks give you interest in bank accounts and stuff like that. So this ends up leveling off, and it ends up leveling off at the value of E. So E is used a lot of times in financial interests, no pun intended there, but it's often used in financial stuff, but it's also used in anything organic that can grow or decay constantly. So think about, like, let's say you are a biologist doing some sort of medical study on hair growth. Our hair does not just grow when we eat, right? Our hair is constantly growing. And so if we were doing some sort of study on hair growth, E would pop into our mathematics at some point. Same thing with like bacteria growth or decay. If you're studying how quickly does a cancer cell die when it's in the presence of this drug, without a doubt, E would pop into that calculation because, biological organic materials do not, they are continuously kind of growing or decaying. So now that you know what E is, let me go back to this. All right, all right, 2.71828, blah, 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 blah. Very similar to pi. If you wish to memorize digits, you can, but you don't need to. We are going to truncate it at 2.718 primarily. The good news is your calculator has this built in, so there's a button for it. So when we actually go to use it in calculations, you're not going to need to truncate it. You're going to use the button. When we graph with base E, when we graph with E's, we will truncate it all the way down to like 2.7. All right, so it'll be something bigger than growth base 2, but smaller than growth base 3. All right. So this is another illustration. This one's in your notes, but you can kind of see this is that equation that he was writing down. And as the n value gets larger and larger and larger, even if we go all the way up to 100,000 and we plug in 100,000 for n, notice that it's just getting closer and closer to 2.718282828, blah, blah, blah.
Never equals it.
What's that?
Never equals it.
And it never equals it. And this illustrates that. So the E is the asymptote. And this is asymptotic behavior. And so that's where Bernoulli realized, wait a second, it doesn't seem to matter whether I compound it 10,000 times or 100,000 times. It's getting bigger, but it's sort of leveling off at a particular value. And so that's where this asymptotic behavior starts to come in. Things you need to know about E, like I just discussed, there are real world quantities that grow and decay with a base of E. And so tomorrow we get into sort of word problems, and that's where we'll see some real applications of where E can play a role. Today we're just going to be doing some basic graphing and just working with the number E. When we graph growth and decay with base E, it'll be a lowercase e, and I do want you to see how to differentiate between growth and decay. When it's growth, it will be base E with a positive exponent. That's how we will indicate growth. If it is decay, all the decays we've seen up till now have mostly been fractional base values, like a 1/2 or a 1/3. This will be E to the negative X. So this is that whole like X flip turns a growth into decay situation. You're not going to see this like this, even though that's equivalent to that. Okay, these two things are equivalent. You're just never going to see it as 1/E. You're going to see it with a negative exponent. And then lastly, when we do our graphing, we will go ahead and truncate it to just 2.7. So we're going to be graphing more decimal points than you've seen on A and B. I know on B, you probably saw a few more fractional value points than you saw on 9A. And I think this question came up yesterday, but I want to go ahead and clarify it. when you are plotting points that are not whole numbers, obviously you're approximating their location, but I need you to do one of two things so that I know that it's in the right spot. I need you to either label that ordered pair, so put an ordered pair label on that point, or if you're using that t-table, just show your t-table. Make sure your t-table is showing what points you are plotting. That is how I will know that you've, been plotting the right points. All right. So let's just go through these real quick, make sure that we know in any kind of form whether it is growth or decay. So if I have a base e to the power of 2x, is that going to be growth or decay?
Growth.
That will be growth because the 2 is positive. What about 2, base 2, to the power of negative 3x?
Decay.
That will be decay. What about negative 3/5 times e to the 0.54?
Decay.
It's growth. Growth.
Notice that the only differentiator was whether it was positive or negative, not the magnitude of the number. So the fact that the number is a decimal doesn't change it from growth to decay. This is still growth. Remember that fractional exponents are like radicals. What about this one? You got a 2/3 to the negative x.
Growth.
That one's actually growth. A 1/2 e to the negative x.
Decay.
That one would be decay. And then negative 4 e to the 0.75.
Growth.
That one would be growth. Now this one would be growing down. It would be growing negatively. Some basic operations with e will show up today just so that you know kind of how to work with this number. When you see the e, we can treat it just like an x, right? It's a placeholder for a number. We just happen to know what number it is. We can apply exponents to a base e, just like we would apply exponent rules to base x or base 3 or whatever. So if you were simplifying this problem, you would go ahead and reduce the 18 and the 6 to get a 3 on top, and then you could go ahead and reduce the base e's using exponent rules and get e to the 7th on the bottom. For this one, the 1/2 will distribute to all 3 bases. So on the top, I would end up with e to the 4th. What is 16 to the 1/2 power? Right? This is a square root in disguise. So the square root of 16 is 4. And then e to the 2. And then these would go ahead and reduce each other. So I would end up with e squared over 4. If you have your calculators handy, I do want you to look and see where the E button is. We definitely will use that tomorrow. You might want to use it today. All right, so this is what we want you to look for. It is on the LN button, which is just to the left of the 7 and the 4. So try it out. If you do e to the power of 1, you should get approximately 2.718. So you can make sure that you're doing it right. If you look carefully, there's actually a lot of other e's on your calculator. And I think that there is one more. So also, there's one, I believe on the divide sign. On the divide button. So that one also works. You can double check that by just doing e to the power of 1 and making sure it comes out. There are a couple other e's that don't work. Okay, so be aware that those are the only 2 that have the built-in value of Euler's number. So when we graph, literally it's going to be exactly the same as what we've done the last 2 days. So that's awesome. It means that we just get to keep kind of using what we've learned and get better at it. The equation is going to look the same. You've got an A, an H, and the K. They all do the same things as before. You do want to remember that e to the positive x would be a growth equation, and e to the negative x would be a decay. Now, the way that I'm going to be doing these graphs, you're just going to be doing a changes to the t-table. But when you look at the equation and you see that it should be growth or decay, that should help you make sure that when you connect those points with the curve is doing the right thing. Like, is the curve falling flat or is it growing away from the asymptote? When we go to graph these, I'm going to ask you to just strip away the A's, the H's, and the K's, and we're going to use this equation to make our t-table. And it would be perfectly okay for you to just kind of write it like this and consider it like that. So the parent t-table will always be, a 1, a 0, and a -1. And so this would be a 2.7, this would be a 1, and this would be a 1 over a 2.7, which that's kind of hard to graph, right? So let's figure out what that's equivalent to. 1 divided by 2.7 is about 0.37. And, if it made sense to go ahead and round that to 0.4, I think that would be okay. Now, when we go to graph these on the day of the quiz, you won't be able to have your graphing calculator on the graphing page, but you could use one of these scientific ones, okay? So if you're having to do 1 divided by 2.7, you could have something like this to do that with. All right, let's try graphing one of these. So right off the bat, I'm going to start with this and recognize, okay, my horizontal asymptote is going to be at y equals 2, and we can go ahead and graph that. Now, there is this other change here. Is this negative here going to be a change to the x's or a change to the y's? That is a y change. And then this plus 2 is actually also a y change. Okay, now I'm going to ignore those for right now. Okay, so I'm going to ignore the blue and the red changes. I'm going to make a t-table for just e to the x. 1, 0, -1, 2.7, 1, and approximately 0.4. Now I can apply these changes to this t-table and I will have my points ready to plot. Do you think it matters whether I do the blue or the red first? Because it's been a while since we've had 2 y changes. So, this is a multiplier, right? And this is an add? So does it matter whether I multiply or add first? Is there an order that I'm supposed to follow? Yeah. So I have to follow the order of operations. So I will actually have to multiply by -1 first. So that becomes a -2.7. That becomes a -1. That becomes a -0.4. Then I can add 2. And so that would be a -0.7. This would end up being a 1. This would end up being a 1.6. All right, so I'm just going to go and plot my points. Now, I'm expecting a growth equation. So when I plot those points, I'm going to look for that pattern. Over 1, down 0.7, so like here-ish. Over 0, up 1. Over -1, up 1.6. Okay. Now, when I plotted those points, the order in which I plotted them, they were going up. But this is a growth equation. It's below the asymptote, so it's going to be flat first and grow away from the asymptote. It's just growing negatively. Our domain is -infinity to infinity. And that's always the case. What impacts our range? Good, the asymptote. So I am always below the asymptote. So I go all the way down to negative infinity. But careful here, our brains are gonna think 2, negative infinity. But the lower number has to come first. So negative infinity, 2. The y-intercept, I have it from my t-table, 0, 1. If it's not in your t-table, just plug in a 0 for x and figure it out. Horizontal asymptote is y is 2. So this should be very, very similar to what you have been doing. In this case, let's do 1 decay, so we can see what that would look like. I'm going to use the basic parent t-table, okay? So I'm stripping away the negative on the x. When I build this basic table, I'll have a 1, a 0, and a negative 1, 2.7, 1, and approximately 0.4. Okay? Now, this is an x change. How will it change my x's? It'll flip them. Yeah, it'll make them all the opposite. So I have to multiply it by a negative 1. And what will end up happening is that this should decay when I go and graph it. This right here is a y change. And so then I would multiply all these by 5. And this is where I wouldn't expect you to do this multiplication in your head. You could certainly reach for a calculator on that. 2.7 times 5 is 13.5. This would be a 5. And this would actually be a 2. And now I'm just going to plot my points. Let's see. My asymptote did not move. That's still at y equals 0. I've got the point over negative 1 up 13.5. So there's 11, 12, 13, 14, somewhere up there. Over 0 up 5, 1, 2, 3, 4, 5, and over 1 up 2. And there's our decay equation. Domain is infinity to infinity. Range in this case is everything above 0. Soft brackets on both, because you never equal the asymptote. Y-intercept is from our t-table, 0, 5. And the horizontal asymptote is at y equals k. And so that's it. As long as if you leave this t-table on the side of your graph, I can grade that. I can look to see that you plotted them correctly, and you're going to be fine. All right? So that's it for today.